Hi, today's paper is Novelty Detection in Reinforcement Learning with Word Models. In this talk, I will explain how reinforcement learning agents can use word models to detect unexpected changes in the environment during development. I'm KyeongMin Kim, and I am a PhD student in the IIXL lab at Korea University. Now back to the paper. The core problem is simple. Other agents are usually trained to perform well in a training environment. However, during development, if the appearance or dynamics of the world suddenly changes, the run policy may no longer be reliable. This paper addresses the problem using world models. If the state predicted by world models and the state actually observed from the world environment become significantly misaligned, the agent can interpret this as a sign of novelty. The key meaning of this paper is that world model can be used not only for policy learning or planning, but also as a safety monitor during development. The motivation of this paper starts from a basic assumption in reinforcement learning. In many other settings, we assume that the training environment and the evaluation environment follows the same transition dynamics. However, in real development, the world is not always fixed. For example, in a game, an object may change color, an obstacle may appear, or a door that used to open may no longer open. In robotics or real-world systems, friction sensor, actuator, or the surrounding environment may also change. The problem is that the agent may continue executing the same policy without realizing that the world has changed. If the world has changed but the agent cannot detect it, the policy may no longer be safe or reliable. This paper argues that before adaptation, the first necessary step is detection. In other words, the agent must first recognize that the world has changed before it can stop, adapt, retrain, or ask for human intervention. In this paper, novelty is different from a simple outlier or temporary sensor noise. Novelty refers to an unexpected change that occurs at inference time, and it usually means a persistent shift in the observation space or environment transition dynamics. For example, visual novelty refers to changes in object color, textures, or visibility. In Atari Freeway, if cars become invisible, that is a visual novelty. Dynamics novelty means that the world responds differently to the same action. For example, a door may open in the original environment, but after novelty occurs, the same actions may no longer open the door. The important point is that novelty is not simply the same as a reward drop. If we wait until the reward decreases, it may already be too late. Therefore, this paper uses prediction mismatches in the word model as an earlier signal of novelty. There are several reasons why existing anomaly detection methods are difficult to apply directly to reinforcement learning. First, our data is not IID, that is independent and identical distributed. The meaning of an observation depends on which state the agent was in, which action it took, and what happened before. Second, threshold turning is difficult. Many anomaly detectors require a threshold that determines when a difference is large enough to be considered anomalous. However, in novelty detections, the key assumption is that we do not know in advance what kind of novelty will appear. So, tuning a threshold using novelty examples can conflict with the problem setting. Third, using reward drop is also limited. In sparse reward environments, novelty may occur long before the reward changes. Also, reward drop only tells us that performance got worse. It does not directly tell us which transitions or part of the world changed. Therefore, this paper uses the internal prediction of world models to obtain a more directly signal. A world model can be interpreted as the agent's expectation about the world. Given the current state and actions, the world model predicts what the next state should look like. Under normal conditions, the dynamics run by the world model and the actual dynamics of the environment should be similar. Therefore, the predicted state and the observed state should be reasonably aligned. However, when novelty occurs, this alignment breaks. For example, in the world run by the agent, a certain action may be expected to open door. But in the actual world, after novelty occurs, the door may no longer open. In this case, there will be a large mismatch between the world model's prediction and the actual observation. This is the main intuition of the paper. If the world predicted by the model and the world actually observed by the agent are different, the agent may have encountered a new world. This paper mainly implemented novelty detection on top of the Dreamer V2 world model. Dreamer V2 compresses image observations into latent states and uses the RSSM to model history and dynamics. The important distinction here is between the prior and the posterior. The prior is predicted from the recurrent hidden state before the model uses the current observation. In other words, it represents what the world models expected based on history. On the other hand, the posterior is inferred using both the recurrent hidden state and the embedded recurrent observation. So it represents the latent state collected by what the agent actually observes. For novelty detection, the mismatch between the prior and posterior is important. The prior corresponds to the agent's expectation, while the posterior reflects what actually happened in the world. Now, let's look at the core detection pipeline. First, the agent executes on actions in the current state. The world model predicts what the next state should be after that action. This prediction is represented as a prior latent state. Then, the actual next observation arrives from the environment. Using this observation, the model comes to the posterior latent state. Under normal conditions, the prior and posterior should not be very different. But when novelty occurs, the prior predicted by the world models and the posterior inferred from the real observation can become significantly different. This paper uses that mismatch as a novelty score. The larger the misalignment between the hallucinated state and the true observed state, the more likely it is that novelty has occurred. Here, an important question arises. Why not simply use a low prediction error and classify transitions as novel when the error is large? The reason is that the world model is not perfect even under normal conditions. Especially in uncertain states, predictions error can be larger even when there is no novelty. So, a simple threshold can easily produce many false positives. This paper addresses this issue using a K-R bound. It measures the difference between the prior latency distribution and the posterior latency distribution using K-R divergence. Then, instead of manually choosing a threshold from novelty examples, the method uses a K-R-based bound. If the prior posterior mismatch violates this bound, the transition is flagged as unnovel. The key point is that the method does not require manual threshold tuning using novelty examples. Instead, novelty is detected when the mismatch violates a bound. The, the exam sorry. The experiments are conducted in three groups of reinforcement learning environments. The first group is mini-grid. The paper uses NobGrid, which adds a novelty to mini-grid environments. For example, lava can be introduced, or a door can behave differently from what the agents learned during training. These examples test whether the method can detect changes in the environment transition dynamics. The second group is Atari. The paper uses Hack Atari to modify Atari games in controlled way. For example, in Freeway, cars can become invisible. This is a visual novelty because the game dynamics may still exist, but the agent's observation becomes different from what the world model expected. The third group is DeepMind control shoot. Here, the paper uses real-world RL shoot to introduce noise or dynamics shifts into continuous control task. This setting is useful for testing whether the method can also detect changes in physical transition dynamics, not only visual changes in game environments. The paper compares the proposed method with RIQN, which is an RL focused novelty detection baseline. It also uses PPMare as an evaluation baseline. PPMare is based on the reconstruction difference between the Dreamer V2 prior and posterior. Overall, the experiments are designed to test whether the proposed K-bound method can detect both visual novelty and dynamics novelty, while keeping false positive low. The paper mainly evaluates the methods using three metrics. The first metric is average delay error, or ADE. This measures how quickly the detector identifies novelty after the novelty becomes observable. A lower ADE means faster detection. The second metric is false positive rate. This measures how often normal translation or incorrectly classified as novelty. This is important because the novelty detector can constantly raise false alarms would not be practical during development. The third metric is AUC, which measures how well the novelty score separately nominal transitions from novel transitions overall. The main result is that the proposed K-bound method keeps the false positive rate low while still detecting novelty quickly. In many ways than Atari environments, the method generally achieves strong performance compared to the baselines. In DeepMind control tasks, RIQN can sometimes detect novelty faster, but it often produces more positives. Another important point is that the proposed method does not require manually tuned novelties thresholds using novelty examples. Instead, novelty is detected through violation of the K-base bound. The paper also showed that the general idea can be extended beyond Dreamer V2. For example, the K-bound approaches can also work with transformer-based world models. Overall, the result suggests that world model-based novelty detection can provide a practical deployment safeguard while maintaining low false positive rates. Okay, to summarize, the main takeaway of this paper is that the low-level world model can be expanded beyond planning and post-learning. Traditionally, world models are mainly used to predict future trajectories or improve sample efficiency in reinforcement learning. However, this paper shows that the world model can also be used as a novelty detector. The key idea is simple. The world model represents the agent's expectation about how the world should behave. If the actual observation consistently disagrees with the expectation, the agent may have encountered a changed or previously unseen environment. This is important for deployment safety. Before adaptation, retraining, or human intervention, the agent first needs to recognize that the world is no longer behaving as expected. Of course, there are still limitations. The quality of novelty detection depends heavily on the quality of the world model itself. If the world model is inaccurate, the detector can also become unreliable. Another issue is exploration coverage. If the agent did not sufficiently explore normal transitions during training, even nominal situations may later look novel. Finally, the paper mainly focuses on detection. It does not fully address what the agent should do after novelty is detected, such as adaptation, policy switching, or safe recovery. This message of the paper uh, can be summarized in one sentence. If an agent can predict the world, it can also detect when the world has changes. That's all. Thanks for watching.